OB. Just give a feel for measure. What is measure? How much I should rotate this so that it coincides with this, right? So if I rotate this, finally it coincides with this. The amount of rotation that is what is measure of an angle, right? So okay, so you know that right angle is 90 degree, right? Or a straight angle is 180 degree. Does anyone know where did this number 180 come from? Anyone? Any idea? Why did we say why is the straight angle 180 degree? Why is this angle 180 degree? Yeah. Anything? Any guesses? Just you can be double of 90. But why 90 then? Why is this angle 90? We could have defined a right angle to be say 100, no? Isn't that better? In in temperature scales and all. Can you hear me? In temperature scales and all, a measure is 100, right? You take the boiling point 100, melting point 0. You take the boiling point, melting point, define 0 to 100, right? 100 seems to be a more natural division, right? Why this 90? Why do you think we took the 90? Or why this 180? Okay, a clue. A whole angle is 360, right? And this 360 corresponds to some natural phenomenon, something like that. Close some natural phenomenon. Huh? 60 minutes? No. It's one rotation of Earth around the sun, right? That takes around 365 days. So if you consider 360 days, okay, the rotation of Earth around the sun, in one day, how much will the Earth rotate? The Earth is here, the sun is here, right? In 360 days, it rotates one whole rotation. So in one day, 1 degree, right? This measure will be 1 degree, right? So the Earth rotates by 1 degree around the sun approximately. Okay, if that is a crude measure. So that was how 360 came into place. But why do you think this stuck? Why didn't we? There are other measures of angles also. Degree is one of the measures. Then there is centesimal. There are others. But why do you think this stuck? Degree measure. It's easier to work with, right? Why? If you divide it into 2, you'll get 180, which is a whole number. You divide it into 4, you'll get 90. Divide it into 6, you'll get 60, right? But if a whole measure was 100, if you divide it by 3, what will you get? 33.33, right? Divided by 6, some other decimal, right? So 360 has a lot of factors. So you can divide it by 2, 4, 8, 3, 6, 9. You'll still get whole numbers. That is why this number stuck. Okay. So that's a side story. Anyway, so that is how, but you should understand that a whole angle can be taken as anything. We can define it to be anything. We take it to be 360. That is why our right angle is 90 degrees, straight angle is 180 degrees. Not because the right angle is 90 degrees, that's why a whole angle is 360. Okay. Okay. Next point. If you take a circle, okay, you take an arc of a circle, okay, say this part of the circle from here to here. Okay, suppose this measures some x units. Okay, the length of that arc is x units. Okay, and different color. Oh, sorry. Let me take a brighter. Yeah. Okay. So this length supposes x from here to here. Okay. And suppose the angle it makes at the center be some y. Okay. Whatever measure doesn't matter. Some standard measure, either degree, centesimal, whatever. Okay. Now, if I take, say, double this length, one more. If I take one more arc of length x, okay, how much will this angle be? The whole angle 2y. Why is that? Angle subtended by a arc to the center. This length by this ratio angle will remain the same. So basically, whatever length is here, it will be proportional to the measure of angle. Okay, this is not at all obvious. Okay, you can prove this point. Okay, I'm not going to go to the proof, but you need to understand that the length of the arc of a circle is proportional to the angle, measure of angle. Okay, and you should also know that it's not obvious. Can you tell me why it is so? Why should it happen? Why if I take, instead of x, if I take 1.5x, the angle will be 1.5y? Why is it true? Anyone? You can make an approximate proof. We can give an approximate sort of argument. What if this was a triangle? Would your argument hold there? Not necessarily. No? If you have here, so let me name this points O, A, B, O, A, C. So AB, suppose this is 30 degrees. Will AC, the length, will it be double? No, right? It's not true. So in case of triangles, it's not true. But why is it true in case of circle? Think about it. Okay, tell me in the next class. Think about this. Why is the circle circumference proportional to the angle at the center? We'll discuss it in the next class. So, yeah. So we have point number 1. We talked that whole angle is defined as 360 degrees, right? By definition, we take whole angle to be 360 degrees. The second point is circumference is directly proportional to what? Measure of angle, right? Measure of angle at the center of the circle. The third point, if I take two circles, okay, one with radius r, yeah, 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 right. Yeah, that is only if you're taking, okay, so you're telling the circumference is 360 degree, half of that is 180 degree if we take a straight angle, and that will be c by 2. But I'm telling for any angle, you're giving example. First of all, you're giving an example for 2. First of all, why should this happen? Why should this become c by 2? Why should this length become c by 2? You can say, well, it is symmetric here and here, right? That's why this length should be equal to this length. That is one case. But I'm telling you, for any angle, this proportionality holds. You can take anything, half a degree, √2 degree, pi degree, and the length will be proportional. You can prove it. There is a mathematical proof for this. I'll give you a hint, but I want you to think about it a little bit. Okay. The hint is this. Think about dividing this into smaller parts. Okay. And each part, you can think of a triangle. Okay. This is the hint. Go home and think about it. How can you prove it? Okay. The third point is, now if I take one circle with radius r, one circle with radius say 2r, then what will happen to the lengths of the circumferences? They're proportional, right? So the circumference is not only proportional to the angle at the center, the circumference is also proportional to the radius. Okay. Again, you can prove this just like the previous case, but it's not really necessary, but it is interesting. Okay, in the next class, maybe I'll take it up. Okay, think about it. Okay, so based on this, we are going to solve some problems. Let me show you some videos. Has anyone seen this cosmic distance ladder by Terence Tao? Anyone? No. Anyone knows who is Terence Tao? Who is he? Mathematician. Very famous mathematician. Why is he famous? He got his one most famous achievement is, I think he got the international math gold medal when he was 15 years of age or something like that. Very young, basically. And he's a very famous mathematician, really smart. And this is his lecture he gave about distances, cosmic distances. So he's calculating the giving you a background about how ancient Greeks and all these people, they didn't have any instruments to measure. There were no satellites, there were no telescopes, right? But just looking at the night sky, they would make some observations and they would make approximations for radius of the earth, distance between the earth and the sun, all these kinds of distances. So we are going to calculate these things. Okay. And he explains it nicely. So I'll let him do the explanation and then we are going to do the calculation. Okay.
Since they didn't have any technologies on flight through, they could travel a little bit. For example, from Greece, where they would travel to Egypt. And even from Egypt, there was enough of a distance that you could start seeing some constellations in the southern hemisphere that you could not see in Greece. But the constellation was slightly different. And Aristotle realized that the reason for this is because even the relatively short distance from Egypt to Greece was enough to see some curvature of the Earth, and that changed the constellation that you could see. And so that told him that the Earth was not enormously huge. Even with the trip to Egypt to Greece, you could see some of the curvature of the Earth. So the radius was finite. But unfortunately, this argument is also correct, but it didn't really give an accurate measurement of exactly what the radius of the Earth was. So that had to come a little later, about 100 years later. Eratosthenes did compute the radius of the Earth, and he computed it to 40,000 stadia, that's a Greek unit. modern units are 1,600 kilometers or 4,200 miles. That's a very good estimate. That's actually within 8%. Astronomers nowadays who kill for 8% accuracy. But and he had very little, almost no technology to do this, and he got an answer within 8%, which is really fun. And it's an indirect argument as before. And now it was done by looking at the sun. Well, not directly at the sun, but indirectly at the sun. That's it. Okay. So how did it work? So let me put the story before we get. So Eratosthenes knew he wrote a book about a well in Sine. Sine is a town in Egypt, originally Egypt, which had a well. And this well had the funny property that on the summer solstice, June 21st, the longest day of the year, you could look into this well and you could see the sun reflected directly overhead in the water below, even though the well was very deep. Okay, and most wells don't do that, but the well in Sine did. Okay, and the reason for that, ultimately, we now know, is because Sine has the fortune to lie exactly almost when it comes to cancer, which is one of the chief places in the world where this happens, that is the Capricorn in southern hemisphere. So, okay, Eratosthenes read this, but he didn't live in Sine, he lived in Alexandria, which was also in Egypt, but a bit to the north. And so he decided to be a good scientist to try this experiment. He waited until June 21st and looked at the well, and he did not see the sun reflected in the water below. Okay, so the sun was not at an angle. So most people are just going to say, well, that was rubbish, and move on. But the person was going, said, okay, what must be happening? He knew about Aristotle. He knew that this curve. And so the reason why the sun was not reflecting down the well where he lived was because of the curvature of the earth. And he happened to be with a measuring stick, no one, like he was holding the sun down. So he measured exactly the angle, the deviation to which the sun was falling. It was not quite vertical, it was like 7 degrees in power units off the vertical. Okay? And he also knew how far it was to Sine. So merchants going up another the Nile, they had to know how many days it took to get from A to B. They knew how many stadia they would cover in a day. So Eratosthenes would just ask these merchants, and some merchants say he actually paid some graduate students and merchants to walk. But that's apocryphal, but believable. But anyway, he knew that the distance from Alexandria to Sine was 5,000 stadia. And just those two pieces of data, and just a little bit of mathematics, that's already enough to work out the radius of the Earth. And a little bit of trigonometry. And it's triangle with one side of 5,000 stadia, that's enough to work out the radius of the Earth. And
yeah, so okay, let me go back to my screen. Okay, so basically sine is here. I don't know how many of you during lockdown last year there was a zero shadow contest here. Anyone participated? What did you see during the zero shadow day? The sun is directly above you. Okay, every day it doesn't directly come up on you, it goes at an angle. Okay, but on one day or 2 days in a year, the sun goes exactly above your head. So that is zero shadow day. Okay, so for different longitudes, not longitudes, latitudes, it will be on different days of the year. Okay, so it happened that on Sine, suppose that place called Sine, that was on the Tropic of Cancer, and there on the summer solstice, first of all, sun's rays you can think as parallel, right? Because they are very far away, right? So you can assume the sun's rays to be parallel. Okay, and so this if you look at any object here, the shadow will not form, right? Because the sun is right above your head. Okay. So you can think that the sun's ray through here will pass through the center of the earth. Okay. But on the same day, in another place, uh, he measured this angle. Okay. And this angle was 7 degrees. Okay. So I want you to use this as well as the distance between these two places is given as 5,000 stadia. Okay, and one stadia is around 150 meters. So I want you to calculate the radius of the earth from there. Please try and do this. You can discuss with your friends. Okay. Can anyone guess what is this angle? 7. Because these are parallel lines, right? These are alternate angles. This is 7 degrees. You can use this and get the answer. Do you know this distance? 5,000 stadia, right? So 5,000 into 150 meters. How much is that? 7 meters or kilometers. How much kilometers? Huh? 750 kilometers. Okay. So from here to here, it is 750 kilometers. You know this angle, you know this. Try to get the measure from 6,100. Yeah, around that. How do you get that? 7 degree corresponds to. Okay, 7 degree corresponds to 750 kilometer. 360 degree corresponds to. No. Huh? What will 360 degree give you? The circumference, right? What is circumference? 2 pi r, right? So this is 2 pi r. Yeah. So these basically this is proportional, right? So cross multiply, you'll get 2 pi r is how much? 360 by 7 times 750, right? And from there you'll get radius of Earth. So 360 by 7 into 750 by 2. Okay. Whatever this is, you'll get something around 6,100, right? Isn't it amazing? Just by looking at some natural observations. First of all, people didn't know that the Earth is a circle, right? And in this lecture, he talks about why Aristotle thought about why Earth is curved. Turns out he said that basically the stars that you see in the northern hemisphere is different from the stars that you see on the southern hemisphere during the same time of the year. So that's why the Earth had to have some curvature. Okay, but it could have been, we never had an estimate how big the Earth is. Right? This was the first time somebody calculated that, okay, the Earth is so big, the circumference is so big. So that's very significant. Okay, so first thing that we have calculated is the radius of the Earth. So we have calculated radius of the Earth. Okay. So the next thing that we go is the next object which is the next closest object in the sky, the moon, right? So next thing that we are going to calculate is the size of the moon and the radius, the distance between the Earth and the moon. So the radius of rotation of moon around the Earth. Okay, so distance. Okay, so this is going to be another 3 minutes of video. Let me just play it.
And around the same time, Aristarchus, another Greek, was the first to compute the distance to the moon in terms of the Earth's radius. So an indirect measurement. Couldn't measure the distance to the moon directly, but you can measure it in terms of the radius of the Earth. And he said that it was 160 Earth radii. And this is, again, an amazing accurate answer. In fact, it's basically spot on. The moon actually is a slightly elliptical orbit. It varies between 57 and 63 Earth radii, but on the average, Aristarchus was exactly correct. He also computed the radius of the moon. He said that the moon is about 1/3 the radius of the Earth, which is pretty close, 0.33, exactly 0.27. But still, not bad accuracy for. And of course, we know the radius of the Earth. We computed it in the first round, so just for that, we just combine that with the information I just told you, and that gives you the radius of the moon and the distance. Okay, so how did Aristarchus do it? So it is again an indirect argument. To find the distance to the moon, we will use the sun. And once again, we will use eclipses, lunar eclipses first. So lunar eclipses, as I told you already, are caused by the moon passing through the Earth's shadow. Now, how big is the Earth's shadow? Well, the Earth is 2 Earth radii in diameter, and that's basically how wide the Earth's shadow is as well, assuming the sun is far away. But we'll get to that. But the Earth's shadow is about 2 Earth radii wide. And lunar eclipses, well, the Greeks already observed many lunar eclipses. They knew that the longest that a lunar eclipse ever lasted was 3 hours. No eclipse lasted more than 3 hours. This was the maximum. So that means that it took 3 hours for the moon to cross 2 Earth radii. On the other hand, it takes, strangely enough, 1 month, 1 lunar month.
Okay, so that much information is enough. What is this? This is the orbit of moon around the Earth, right? So to move this distance is 2 times radius of Earth, right? To move this distance, we know it is 3 hours. To move the whole circle, do we know how much it is? 28 days, right? Use that information. See if you can get something. They're proportional, right? Good. So let me just tell you. This distance is 3 hours, right? It takes 3 hours for this distance. Okay, just can you look? This distance is 3 hours, right? And the whole circle is 28 days, right? So 3 hours, we know that the moon covers a distance of 2 times the radius of Earth. So this is time and this is distance. Okay. So in 28 days, which is 28 into 24 hours, right? These many hours. How much is the distance? The distance will be this whole circumference. And this whole circumference is, if you take this distance, the distance between the moon and the Earth, right? In terms of this, the whole circumference is 2 pi times d, right? So 2 pi times this distance between moon and the Earth, which is basically the whole circumference, is this value, whatever you get here, right? Because they are proportional. So if you cross multiply this, you'll get 28 into 24 by 3 into 2 times radius of Earth. Okay, and radius of Earth we have calculated here something around 6,100, 6,400, whatever. Okay, so this distance between moon and Earth, you can check in your calculator later at home. It will be approximately 60 or 70 times radius of the Earth. Okay, so that is the distance between the moon and the Earth. It will come to around 40,000, 42,000 some kilometers. Fine. That's the distance between the moon and the Earth. What's the next thing? This we calculated. This is pending, right? Size of the moon. So I won't play the video. I'll just tell you. Have you noticed you notice the sun setting on the beach, right? Have you noticed how long it takes for the sun to set? From the, so suppose this is the ocean, okay, you have the sun here. So from this position where it just touches the water to the part where it goes down, how much time does it take? Have you ever observed this? No? Make a guess. How much time will this take? Make a guess, random guess. 2 hours. Huh? 20 minutes, 7 minutes. It's 2 minutes. Okay, it takes 2 minutes for the sun to set. Next time you go to the beach, you just observe. You'll see exactly in 1 minute, exactly half of the sun goes down, and another minute, the whole sun goes down. So next time when you're in the beach, do make this observation. Okay. Anyway, so it takes 2 minutes for the sun to set. Okay. And also, if you look at the sky on a solar eclipse, you see that the moon perfectly fits the sun, right? So the angular size of the sun and the moon is exactly the same, right? It turns out just by luck that the moon, but there are these annular eclipse and all where you can see a small band around the moon. Do you know why that happens? Why is there an annular solar eclipse? Huh? Does the moon shrink in size? Huh? It has a elliptical orbit, so it sometimes is further away from us, sometimes is closer to us. So when it is further away from us, it appears smaller. That's why you can see in an eclipse, you can see a small ring around the moon. Okay. But in general, you can think of the moon size to be approximately the sun size, okay, in the sky. So if you look at the moon's apparent motion around the Earth, the moon also takes 2 minutes for the moon to set, right? And how much time does it take for the moon to rotate a whole apparently around the Earth, around apparent motion of the moon, this moon to go all the way, or the sun to go all the way around and come back to the same position? How much time does it take? 24 hours, 1 day, right? So 2 minutes it takes for it to cross this. 24 hours it takes for the whole rotation. From that, you can calculate the radius of the moon. Please try that. Think about it. You can think of it as an apparent circle. Okay. Moon going around. This is the moon going around the Earth. You can think of it. Okay. And it takes 2 minutes for it to set, right? So this distance, and you know the whole distance is 24 hours. So see if you can calculate the size of the moon from that. Yeah, what's it about? Finish, got. Okay, tell me, how do you do it? To cover this, yeah. So this is nothing but the diameter. This is the diameter of the moon. So this distance is the diameter of the moon. So to cover the diameter of the moon, how much is the diameter of the moon? We have that is what we are calculating, right? So 2 times radius of moon. So this much distance corresponds to 2 minutes, right? The whole circumference is 24 hours, right? That is 24 into 60 minutes. So that will give what distance? What is this distance? 2 pi. What is this? Distance between the Earth and the moon, right? This is moon's apparent motion around the Earth, right? So this distance is the distance between the Earth and the moon. Okay. So 2 pi times distance between the Earth and the moon is equal to this cross multiplied ratio, right? Which is 24 into 60 into 2 times radius of moon divided by 2. Okay. And distance between Earth and Moon we have seen is around 60 times the radius of Earth, right? So this is 120 times pi times radius of Earth is equal to, so this 2 and this cancel, divided by 24 into 60. That will give you radius of Moon. And you can do an approximate calculation. Once, twice, 12 times. How much is pi by 12? Around 3.14. Right. So radius of Moon is radius of Earth divided by maybe around 3.5, something around 3.5, right? So Moon's radius is around 1/3 the Earth's radius. This observation you just make by this simple fact that it takes the sun or the moon 2 minutes to set or rise. Okay, so you've all got a good sense now of how big the Earth is, what's the distance between the Earth and the Moon, how big the Moon is. Okay. Next class we'll talk about distance between Earth and Sun. I'll stop with distances for now. Okay. Because you might need some other the sine cosine things. So yeah, we'll move to Sun in the next class. Okay, Sun is also very interesting. The kind of observations that he talks about is quite interesting. Okay, so that is about distances. And in all of this, what is important to see is the only fact that you used is this, that the circumference or the arc length, I should have written arc length here, arc length is proportional to the measure of the angle at the center. Okay, and in all of these cases, we've seen that the measure, this 3 by 24, which we did, 3 by 28 into 24, that will give you the measure of the angle. So this angle divided by the whole angle. Effectively, that is the ratio we took by taking this time, 3 divided by 3 hours for the lunar eclipse, 28 days. Okay, that is effectively this ratio, which is the ratio of this angle to the whole angle. Right? So we have only used the fact that the arc length is proportional to the measure of the angle at the center. Okay. Okay. So that's a very important thing. And so one more measure that we come up with, do you know how this, in physics, you must have learned what is a foot, 1 foot length, 12 inch. But where did this foot come from? The measure of foot. Probably from some person's feet, right? The measure of feet. But what was the problem with this foot measure? It's not standard. The foot measure can change, keeps varying from person to person. So we cannot have this as a standard measure. Similarly, in terms of measure of an angle, we take some sort of arbitrary value. At least it doesn't vary. There we define a whole angle to be 360, but we can make a better measure, and that measure is called a radian. Okay, and the radian is defined as, if you take a circle, take an arc with arc length equal to the radius of the circle. Okay, the measure that this arc length makes is defined as 1 radian. Okay, and radian is denoted by this. Okay. So the measure that 1 radius makes at the center is defined as 1 radian. So how much is the whole circle length? How much is the circumference? Circumference is 2 pi r. So how much will be the angle made at the center? 360 in degrees. What about in radians? It is r corresponds to 1 degree. If you take one more r, 2r will correspond to 2 radians, right? So the whole circumference is how much? 2 pi r. So how much will be the measure? 2 pi radians. So the whole circle corresponds to 2 pi radians. Okay. Half a straight angle is pi radians. A straight angle is pi by 2 radians. Okay. So we'll get more comfortable with this in the next class. Okay, but this is how you define a radian. The radian is defined as the angle made at the center by arc length equal to the radius of the circle. So you can convert degrees to radians and all these things. Okay, just by this proportionality. Can you just quickly do this? Convert 18 degrees to radians. Don't tell the answer. Please, all of you, I want to make sure that all of you know how to convert degrees to radians. Yeah, how do you do this? 360 degree corresponds to 2 pi radians. So 18 degree corresponds to how much? That's all. Okay, you cross multiply, you'll get 18 by 360 times 2 pi, which is, how much do you get? Pi by 10 radians. Okay, that's how you convert degree to radian. Similarly, you can convert radians to degree. Okay, just the opposite manner. Okay, clear with everyone? There are some workbook problems, I think you can do this. Okay. If an angle, if an arc length of S makes an angle of say some alpha radians at the center, what's the relation between S and alpha? There's this circle of radius R. Okay. This arc length S makes an angle alpha at the center. What's the relation between S, alpha? How do you get that? 1 radian. So if you say distance or arc length, so 1 radian measure is 1 radian. So we have S, which corresponds to alpha. So alpha is equal to S into 1 by R, or S is equal to R times alpha. Okay. S into 1 by R will give you this radian. Did you understand? 1 arc length corresponds to 1 radian, right? So we want to find how much this arc length corresponds to. It corresponds to alpha, right? So you cross multiply, or you can take proportionality. So R by S is equal to 1 by alpha. Okay. This by this is equal to this by this, right? So you'll get S is equal to R times alpha. That's the relation between arc length, radius, and the angle at the center. But this angle has to be in radians. What about area? Do you know? Anyone? Area of a sector. Calculate and give me the area of the sector in terms of alpha r. Find the area of this sector. What's the whole area of the circle? Pi r square. That corresponds to what angle? 2 pi radians, right? Now, for alpha radian, you need to calculate the corresponding area. Huh? How much is that? It's just proportionality. Whole circle is pi r square. That corresponds to 2 pi. So corresponding to alpha, how much is the area? That's all. Calculate. So the whole circle is pi r square area. Angle is 2 pi. Right? And you need the, for alpha angle, you need to find the area. Right? So it is alpha into pi r square by 2 pi. And pi cancels, so we'll get half alpha r square. That is area. Okay, that's the formula for area. Now we are going to get into the actual trigonometry. So first we are going to see the general definitions given by your general textbooks. Okay, the high school definition of uh, sine, cosine, tan. These are trigonometric ratios. Okay, and so basically trigonometry is nothing but similar triangles, right? Anyone doesn't know about similar triangles? All of you know what similar triangles are? Similar triangles are triangles which are either expanded or shrinked. Okay, so one triangle is like this, another triangle like this. These two are similar. What is the relation between two similar triangles? The sides are proportional and the angles are equal. All the three angles are equal. Sides are proportional. In congruent triangle, sides are also equal, but here sides are not equal. Sides are proportional. That means this length by this length will be equal to this length by this length will be equal to this length by this length. Okay, sides are proportional. Okay, so now if you take two right angle triangles, say A, B, C, D, E, two right angle triangles. This angle is X. Are these are there two triangles similar here? Which are the triangles? A, triangle ABC is similar to which triangle? DBE. So triangle DBE is similar to triangle ABC. Okay, so this big triangle is similar to this small triangle. So you can take some ratios now. You'll see this ratio by this ratio is equal to this ratio by this ratio, right? Or let me take this by this. Okay, what are these sides called? This side is called opposite side. This side is called adjacent side. Okay, so opposite to this angle. Okay, this angle opposite is this opposite side. This side is anyway the hypotenuse, right? In a right angle triangle, you know that this is a hypotenuse. This side is the adjacent side. Okay, it is the only, there are two sides which are adjacent to this angle. One is this, one is this. But this is already the hypotenuse. Okay, so this is the adjacent side. And this side is the opposite side. Okay, so we are going to take in this triangle the ratio AC upon AB. This length upon this length will be equal to this length upon this length, right? Which is equal to DE upon BD. And for both these triangles, AC and DE are the opposite sides, right? So this is opposite, and AB and BD are the hypotenuse, right? So for both these triangles, this is this ratio opposite by hypotenuse. Okay, so if I take any triangle, this ratio opposite by hypotenuse will remain the same. Okay, any triangle with this particular angle, it can be this triangle, it can be this triangle, it can be this triangle, the opposite by the hypotenuse will remain the same. It doesn't matter which triangle you take. Okay. So that's why we give a name to this opposite by hypotenuse, and it is named as sine. Sine of an angle, SINE. Okay, so sine of x is given by the opposite upon the hypotenuse. Okay. Similarly, there's another ratio that you can take, which is this by this. Sorry, this by this will be equal to this by this, right? And that is, this side is what side? Adjacent side. So the adjacent by the hypotenuse this is called the cosine of an angle. These two ratios are enough for us. This we get from the ratio. What's the ratio? BC by AB equal to BE by B. Right? This by this is equal to this by this. That is the cosine of an angle. Okay, don't worry about these terms. If you have not heard them before, uh, nothing to worry about them. Okay. Okay. So we are going to take some standard angles and we are going to find the sine cosine. Do you know how to do 45 degree? Huh? Forgotten? Let's quickly revise. Okay. So 45 degrees, suppose you take a right angle triangle with 45 degree. What's the opposite? What's the other angle? 45. Okay. So what will be sine of this? Let's forget about this angle for now. Sine of 45. If this is x, what will BC be? BC also will be x. Why? This angle is also 45. That means it is an isosceles triangle. Base angles are same, so side length should also be the same. If this is x, this will be x. You can calculate AB square is equal to BC square plus AC square, which is x square plus x square, which is 2x square. Right? So AB is root of this, which is root 2 times x. So this length is root 2 times x. So sine 45, what is sine 45? Opposite. What is the opposite to this angle? This AC, right? So AC upon hypotenuse, AB. Right? So that is AC length is x, AB length is root 2x. So it is 1 by root. Cos 45, it will be the same, right? You'll get BC upon AB, which is x by root 2x, which is again 1 by root. Okay, this adjacent by hypotenuse. If anyone is not understanding, please stop me, okay? Okay. Anyone wants me to repeat any of this? Huh? Sorry? Can't hear you. Cosine. How we got this? Cosine is adjacent, we are seeing of this angle, right? Which is adjacent by hypotenuse. So it is BC, adjacent is this length, hypotenuse is this length, AB. And BC, the length is x, hypotenuse length is root 2x. Okay, and x cancel, so I'll get 1 by root. Fine? Okay. So we know the angle sine 45, cos 45. What about 30 degree, 60 degrees? Do you know how to calculate 60 degrees? Sine and cos? Sorry? Yeah, you can copy. think about 60 degree. How do we do 60 degree? Sine of 30 plus sine of 30. Sine 60 degree. What triangle should we take? Here we took a equilateral triangle, right? Isosceles triangle, sorry. You have to take a equilateral triangle. Sorry, I gave away the answer. Okay, what happens if we take the equilateral triangle? Angles are 60 degree. But where do I get a right angle? We have to take scaling. You have to draw an altitude. Okay, this will give you a right angle. Okay. What's the remaining angle here? 30 degree. So now this is a what is this triangle ABC? Equilateral. So if I take this side length A, this side length A, how much is this length BD? A by 2. Right? So now calculate sine 60, cos 60, sine 30, cos 30. Calculate all these ratios. All of you. Sine 60 is root 3 by 2, right? Cos 60 is half, sine 30 is half, cos 30 is root 3 by 2. Okay, let's move on. So one problem with this, what is the one problem with this definition? Opposite by hypotenuse. It's only for right angle triangles. So the angle for which we define sine of some angle, cos of some angle, that angle, what is the value of that angle? What value can that angle hold? This angle between 0 and 90, right? So it is only acute angle. So this definition holds only for acute angles, which is a problem, right? We need these definitions of sine, cosine, tan. You can do that at home, remaining thing. Okay. So we need this definition of sine, cosine, tan, cosec, whatever the other definitions for all angles. Okay. We don't want it to restrict it only between acute angles. So we are going to give a more general definition. Okay. That is the unit circle definition. Okay. So this is a definition which will hold for all real numbers. So first you take your coordinate axis. Okay. And we take a circle within this axis. Okay. This is our x-axis, y-axis. And we are going to take a ray from origin, making an angle, say alpha. Okay. So let this ray meet the circle at a point P. This is a unit circle. What does unit circle mean? Radius is one unit, whatever it is. Now let the coordinates of this point P be x, y. Okay. Now you drop a normal on the x-axis. Okay. Can someone tell me what is sine of alpha? Sine of alpha in terms of side lengths, side names is Pn by OP. How much is Pn? What is the length Pn? Pn is the y coordinate, right? This is the x coordinate. This is the y coordinate. That is how you plot a point x, y, right? So Pn is the y coordinate. OP length is, how much is this length? Radius. How much is the radius? 1. We told it's a unit circle, right? So y by 1, right? Or y is equal to sine of alpha. Okay, this is the new definition that we give, sine of an angle. Okay. So what was the definition? We took a unit circle, we took a ray making an angle make alpha with the x-axis, with the positive direction of the x-axis. We saw where this ray intersects the unit circle. Then the y coordinate of this point will give sine of the angle. What about cosine? In terms of side length, it is ON upon OP. Right, ON is the x coordinate. So your new definition for x, for cosine alpha, will be x, the x coordinate of this point. Okay. Sorry? Sine, how is it y by 1? This is 1. Denominator is 1 because the radius is 1. Yeah. So the radius is 1. Okay. Any doubts with this? Okay. Now, for what angles does this definition hold? Can you think of? Is it only acute angles? Can you draw a ray with obtuse angle? You can still draw a ray, right? You will still get a point of intersection. Okay. Will it work for negative angles? Can you draw minus 30 degree? Minus 30 degrees in the clockwise direction, right? Positive is an anti-clockwise rotation. Negative angle is a clockwise rotation. Okay, so minus 30 will be this. Okay, you will still get a point of intersection. The x coordinate will correspond to the cosine of minus 30. Y coordinate will correspond to the sine of minus 30. Is that clear? Okay, so now with this, we are going to make our next definition, which is tan of alpha. Anyone? What is tan? In it is adjacent, opposite by adjacent, right? So in this case, it is Tn upon On, right? Which is equal to y by x. But can we define tan for all? Does this definition hold for all values? Is there a problem with this? Where is the problem? When this ray goes like this, the x coordinate is 0, right? So when the denominator is 0, is the ratio defined? No, the ratio is not defined. So this tan is defined only when x is not equal to 0. Okay, where is x equal to 0? When this ray is either like this or downwards, right? What is this angle? Upward. In terms of radians, pi by 2. So at pi by 2, we cannot define. Which other angle we cannot define this at? Minus pi by 2, right? Why? This angle is pi 0. This angle you slowly increase to pi by 2. This is negative angles, right? So this angle is minus pi by 2. Any other angles? 270 degrees, right? Which is in terms of, right? This is 180 degree. This is 270 degree. 270 degree in terms of pi by 2 is how much? 3 pi by 2. Again, minus 3 pi by 2 also won't work, right? Because this is minus pi by 2. This is minus pi. this will be minus 3 pi by 2, right? This angle will be minus 3 pi by 2. So can you make a uh, general term for this? For what values is tan not defined? Give me a general thing for this. X is equal to 0, but we found for what angles, right? So tell n pi by 2 when n is odd. But can we make that instead of n, can you tell something else so that it is odd for all values? So Siri, no, is suggesting we write n pi by 2. But if you substitute n is equal to 2, well, this won't work, right? But can you tell some other term instead of n pi by 2? 2n plus 1, right? 2n plus 1 will ensure it is always odd, right? So for 2n plus 1 pi by 2, where n is what? n is a whole number, integer, right? So where n is an integer, is it positive integer? Negative integer is also fine, no? So for example, if you substitute n is equal to 0, what will you get? Pi by 2. N is equal to 1, 2 plus 1, 3 pi by 2. N is equal to 2, 4 plus 1, 5 pi by 2. Right? So you'll get all this side. N is equal to minus 1, minus 2 plus 1 is minus pi by 2. Right? Minus 2 plus 1 is minus 1. N is equal to minus 2, minus 4 plus 1, which is minus 3 pi by 2. Right? So 2n plus 1 pi by 2 for all. So let's revise our definition for tan alpha. Tan alpha is given by y by x for all alpha. Okay. For all alpha belonging to alpha can be what? Integer? Real number. It can be a real number minus what values? The set of this values. Right? We should exclude these numbers from the set of real numbers. So minus uh, 2n plus 1 pi by 2, where n is an integer. Okay. From the set of real numbers, we are taking out these numbers. Only then we can define tangent of an angle. Otherwise, tangent of pi by 2, tangent of minus pi by 2 is not defined. We are not going to bother what value of that is because it is not defined. Okay. There's no point of you asking me what is tan of pi by 2. Okay. Now, similarly, we know from our high school that cosec of an angle. What is cosec of alpha? Usually defined as reciprocal of sine alpha, which is 1 by, in this case, what will it be? 1 by sine alpha is y, right? So we'll get 1 by y. But is this defined for all values? No. Where is it not defined? Y will be 0. Where is y 0? This ray, this or this, right? Both these cases, the y coordinate is 0 of these points. Right? So give me a definition for cosec alpha. Write a similar definition for cosec alpha. Write a similar definition for secant alpha, cot alpha. Secant is the reciprocal of cos, and cot is reciprocal of tan. So write down the definitions of this. Return your pencil. Arjun, but absent, no? And Dhyan is present.